Regarding the solution of the magic square, and I select this particular strategy. There are a lot of different strategies which are available if you want to solve this. So first of all, I design one parameter which you can modify to express what is the dimension of the magic square you want to generate. After this line, the goal of this line is just to define the variable, the array, we want to assign. So you can see that we have two-dimension elements, so this is a matrix, and the two dimensions are going from 1, the lower boundary, to n, the upper boundary. So we are designing a n multiply n array. This array is a variable, and I can say that all the elements belonging to this array are integer going from 1 to n multiplied by n. The name of this variable is gris, so it's a French name. In addition to the definition of this variable, I define one parameter. That's why here we don't have var keyword, and this parameter is called number magic, and here we have the definition of this magic number. So this is a tip I gave you in the statement. So just here we have the definition of the variable and the parameter needed to define the problem. In addition to these parameters, we need to express the different constraints that are applied on the values of the cells of this matrix. The first one is that we need that all the different cells must remain different. So that's why I include and use all different functions we use, for instance, in 2 plus 2 is equal to 4. I need, of course, to generate all the different that I want to compare with this all different function. So that's why here I have the definition of a list, and here I just have a generator that evolve and generate a list from all the elements of my variable of my array. So the goal here is just to constrain, to check that all the elements belonging to the matrix are different. The two second constraints here are structured exactly in the same manner, so that's why I will focus only on only one of them. Here I have a for-all aggregator. That's to say I need to check that all the elements after all the sub-constraints are met. Here we can see we have a generator. So this generator is modifying this I variable going from 1 to n. So here the for-all will handle n Boolean values. How these Boolean values are evaluated here, that's why we have another aggregator. This aggregator, sum, have as a generator the evolution of this j parameter. And what is the expression of this element? We have here, we want to perform the sum of all the elements of I line and j row. So the goal of this aggregator here is just to evaluate the sum of all elements belonging to the I lane. And as a result, I want to compare this sum with the magic number. If the magic number is equal to this sum, so here all of this thing is equal to true. So here we are making the comparison of each I line with the number, the magic number. And if all of them are true, for all will be true, and the constraint will be okay. The goal of the next line is exactly the same, but now the thing which is evolving is not the line, it's the column. So that's why here I just exchange the index here, and the goal is just not to compare the line, but now to compare the column. The two last constraints are just here to evaluate the sum of the two diagonal. So here this sum just evaluates the first diagonal and compare it with the magic number. If this is okay, automatically the constraint will be satisfied. And here we have the definition of the second diagonal, okay, and exactly the same thing we are comparing with the magic number. The goal here is just to find all the solutions satisfying this definition and these constraints, and if we run it, we can see the different solutions available. There are a lot, okay? So I can stop and I can use a smaller and try to solve a smaller. I save, restart, and here you can see the different solution available. You can check that the sum will be exactly the same and equal to 15, and exactly the same way for the column and the diagonal. So here you can see the different solutions, which are not very numerous, because we have 1, 2, 3, 4, 5, 6, 7, and 8 solutions. And we can see that the system found this solution very, very quickly. So that was for the magic square problem.